Swayam Prabha. Digital India. Educated India.
Good morning. This is lecture number 40, the concluding lecture in module 7, which deals with the analysis of elastic instability and second order effects. If you recall, in the last session we looked at the slope deflection method of analysis, which is a manual method. Now we will look at a more systematic way of solving the same problem using the matrix method of analysis. We will be using the conventional stiffness method. So this is covered in the last chapter in the book on advanced structural analysis. You are very familiar with all these methods, so this is just to remind you that we will be using only the conventional stiffness method here. So if you are using a beam element, which will now be called a beam column element, because we are going to consider the interaction between the axial force and the bending and shear forces and their effects. So it is more appropriately called a beam column element, and so we are switching over from the beam element to the beam column element, with the difference that we now have an axial force Pi whose value is known. Okay, Pi is known in advance. So if you write down the measures of flexural stiffness, they will take this form. Instead of 4 EI by L, we have capital S. Instead of 2 EI by L as a carryover moment, we have R into S, and these are called stability functions. They are trigonometric functions, and if you have a case of axial tension instead of compression, then you have them in a hyperbolic form. You are familiar with this, and so we can easily generate the stiffness coefficients corresponding to the 4 displacements, applying them one at a time. The easiest to apply is when you have a unit rotation at one end. Instead of 4 EI by L, you have SI. The carryover moment will be Ri SI, and then the shear forces come easily as the sum of those two moments divided by the span. If you have a translation with both the ends fixed, then you have an equivalent chord rotation given by 1 by L, and the formulation is similar to what we did for a conventional beam element without any axial force acting. If you recall, if you had a clockwise chord rotation, you have anti-clockwise moments at the two ends. In the conventional beam element, they were equal, and their value was 6 EI by L squared. Instead of 6 EI by L squared, we now write it as S into 1 plus R divided by L. Okay. So if you plug in those earlier values of S equal to 4 EI by L and R equal to half, you will get the same result. Okay. So we have this familiar form of the 4 by 4 element stiffness matrix, and we can easily generate all the parameters. If the axial force is compressive, you have it in this form. If the axial force is tensile, you have it in this form. Now all this we are familiar with. We have actually used this when we did the slope deflection method, except that in the slope deflection method we used what is equivalent to the reduced element stiffness formulation. Now these trigonometric functions are not very convenient to use. So luckily for us, there is a major simplification possible, and let us look at that. So if you have a 6 degree of freedom element, if you had a plane frame element instead of a beam element, here also you have an axial force, but the big difference is you do not know the value of the axial force, So we leave it as F1 star and F4 star, which must be in equilibrium with each other. And also here we are allowing axial deformations, which was not accounted for in the previous case. So you can use this for plane frame problems, and you have the standard 6x6 element stiffness matrix where the flexural components are suitably modified. So what is happening here is the axial stiffness is still not changing, it is still EA by L, but it is indirectly affecting the flexural stiffness components. So it takes this form, and if the value of the parameter mu L, what is mu L? Square root of PL squared by EI, then we can simplify the formulation by expanding these trigonometric functions in a Taylor series form, and so it takes this simple form. If you take the first two terms for a sine function and a cosine function and you plug in these values in the stability function, you get a very beautiful result. You have only two terms and you have a kind of a constant, a linear relationship with pi. So that makes the whole thing very simple. You do not have any more sine and cos, and if you have the hyperbolic functions, then it takes this form. Okay. Now one way to understand this, and it's a simpler way rather than remembering these expressions, is to interpret them physically. So I have shown here in this figure the standard force stiffness values for a beam element. The standard coefficients are shown in yellow color, so you have 4 EI by L, 2 EI by L, 6 EI by L squared as shown there, you are familiar with that. You just need to add or subtract an additional term which involves the actual force P. So it's a tremendous simplification, and what you see is naturally the flexural stiffness terms, the primary term 4 EI by L gets reduced when you have an axial compression, and if the compression is equal to the critical buckling load, it will actually degenerate to 0. So that term is minus 2 pi Li by 15, and the carryover moment on the other side, which is normally 2 EI by L, gets actually increased by a small quantity PL by 30. The assumption is P is constant and you know its value. So you can actually modify the stiffness if you know P. You have an absolute measure of stiffness, and the vertical reactions are easily obtainable from these two moment terms. So you will find that 6 EI by L squared gets adjusted by a factor P by 20, it is a force unit. So you reduce on the left side and you increase on the right side for this. So try to remember these formulations. Of course you do not really need to for your examination, because this portion I am excluding from your examination, this is a little advanced, but you can see that it is quite easy to operate. And likewise you have these correction terms when you apply a translation like this. So if you look at these two terms, the yellow term is your conventional stiffness coefficient. So we will refer to those terms as first order or primary stiffness coefficients, and they build up the primary or first order, which I show with a subscript O meaning first order. KIO star is in the local coordinate system the element stiffness matrix without any actual force influence coming into play. So that is a first order primary stiffness, and now to that you have to add or subtract. We will say we add with the appropriate sign, whether positive or negative, and that term is called the geometric stiffness matrix. Why is it called geometric? Because it is kind of reflecting the geometric nonlinearity in the structure. It actually is looking at the effect of the behavior in the deformed configuration, right. It is only in the deformed configuration the P delta effects come into play, and those effects are second order effects. So you can also call it a second order stiffness matrix, and we can write an expression for it just by looking at these pictures, and you can it takes this form. Okay, so this is your primary, the yellow colored, and this is your second order. Is it clear? We put minus plus pi. The default is minus if the pi is compressive, but it is positive if pi is tensile, because you know the primary stiffness gets actually enhanced when you have axial tension. So we have actually simplified the whole problem so beautifully. It is very easy to now write down the stiffness matrix. We are including a correction for the axial force. If you have a plane frame element, you can do exactly the same thing, only thing now instead of a 4 by 4 matrix you have a 6 by 6. So it looks like this is your primary matrix, where you have the terms as we did earlier, and now you have this additional term for the geometric stiffness matrix. You will find that the first row and the third and the fourth row and the first column and the fourth column in the geometric stiffness matrix are filled with zeros. The reason is this effect is only for the flexural stiffness terms. The geometric stiffness does not affect the overall stiffness matrix for the axial terms. Axial term is still A by L, no change in that. So that's it. We are now ready to solve any problem. If someone were to give us a value of P, you just have to modify the stiffness and do the same old thing. Okay, but this also gives us a way of finding out the critical buckling load. How do you find the critical buckling load? How do you find the P critical? Well, not in an element, in a structure, once you assemble the structure. So the structure stiffness matrix will look like this after you have assembled it. Okay, there is no I coming in here, you have K equal to KO, which is primary, which is what we got earlier, plus Kg, which is the geometric stiffness matrix for the whole structure. And let us say there are loads acting on the structure, and very conveniently let us apply, they are equivalent joint loads, and let us apply the loads at the nodes, and let there be no moments. If you have moments, or if you have a distributed load, you realize that it really does not affect the buckling load capacity of the structure. You remember when you had primary eccentricity, you started off the lateral deflection at some initial point, then you traced asymptotically the critical buckling load, right. So how do you define a critical buckling load for a column?
For which the total stiffness becomes 0.
The stiffness does not become 0. Well, if you had one element you could use that language, but for a structure you have many components in your stiffness matrix. So how would you say the same thing? If you gradually increase the load P, if it behaves in a linear elastic manner, you would find the stiffness matrix also linearly changing, because in this simplified form, in this approximate form, the stiffness coefficients are a linear function of P. So if I add, if I keep P constant and I increase the load, I still have a linear variation. But as I keep doing that, at some point something happens and the structure buckles. That is called elastic instability. How do I locate that value of P? That value of P for which buckling takes place. What happens to the stiffness matrix? It becomes it does not become 0, that is a wrong word to use.
It does not change.
It becomes, fill in the blank, it becomes in. We have done this earlier in slope deflection method. How did you find the critical buckling load? It becomes singular, then only you get an eigenvalue formulation, right. It becomes singular. So that is how you just have to take the determinant of the overall stiffness matrix and then put that determinant equal to 0, and you have to take only for your active degrees of freedom, obviously, because your equation is Ka dA equal to 0. You solve that, you got an eigenvalue problem. Here you get eigenvectors, not eigenfunctions, because you are dealing with matrices. That is how you solve this problem. Is it clear? So supposing you had distributed loads, do not worry about them, convert them to equivalent concentrated loads, let there be only axial forces in the structure, okay, initially. So if you had what is known as pre-buckling moments, it is okay, you keep them aside for the time being, because they will they do not really affect your critical buckling capacity, because you have studied earlier that asymptotically you will hit that value, right. Of course probably your structure will collapse well before that, because you have other non-linearities coming into play. Okay. So the accuracy in the estimate of the critical buckling load can be enhanced by reducing the value of the parameter mu L. Please note those approximations are valid. I mean you can reduce it to just considering two terms in the Taylor series expansion of the sine and cosine function, only if that parameter mu L is small. Now mu L is square root of PL squared by EI. You have no control over P, you have no control over EI, but you have control over L. So if you make your element smaller, you make mu L smaller, and actually you will get more nodes and you will get a better picture of the mode shape also. The mode shape also will look much better. Okay, let us apply it to very easy problems to test out this method. Okay, we know the solutions for these, we know the Euler buckling load for these two cases, they are ideal braced columns. Case A, both the ends are fully fixed against translation and rotation. Case B, they are fixed against translation, but they are free to rotate, it is a pin-pin condition. Okay, what is the value of P critical for this? Pi squared EI by, no, the second case, pi squared EI by L squared, K effective is 1, and the first case 0.5, which means the load will be 4 pi squared EI by L squared. We know that, we know the answer. Let us see if we can get this answer by matrix method. So obviously you need to create some nodes, right. How many elements would you recommend? This is just one element, you will not be able to get the result with one element, you need a, because the two ends have to, there has to be a lateral displacement, no. So you need a node, how many minimum? Well you just need, we will try this out, okay, we will just put one node in the middle. You can divide into 3 elements, you will get a better result, 4 elements even a much better result, but let us check out with just 2 elements whether we get a reasonably good result or not, and that will validate our method. So we will do that, and we will write the stiffness matrix, and we will put the determinant equal to 0 for the active degrees of freedom. Now if I divide this into 2 elements, how many global degrees of freedom will I have? Global coordinates in case A, active global coordinates in case A, if I put a node in the middle, active, well at that node you have a translation and you have a rotation, right, and at the two ends if you are doing a beam element you do not have axial deformations, okay, so you do not need to introduce that degree of freedom. So you just have 2 active degrees of freedom, and for the second case you have those 2 plus you have 2 rotations, so that is it. So this is the first case, I put it horizontally, it does not matter, the column can be made horizontal, okay. I put a node in the middle, so 1 and 2 active, and then of course I have restrained coordinates 3, 4, 5 and 6. Is this clear, right? In the second case I have 1 and 2 as before, but I also have 2 end rotations 3 and 4, and I have only 2 restrained coordinates 5 and 6. Is this clear? It is very simple, okay. What about local coordinates? Well that is a standard beam element, except that we are having a constant axial force P, it is the same P in both of them, it is the same P because it is a single column, and we write down the stiffness matrix which has the first order component which is a standard stiffness matrix, and we put a minus P to bring in the geometric stiffness part. Is it clear? So this we know, these two matrices we have derived. So this is at the element level, okay, at the element level. At the element level the stiffness matrices are always singular, do not worry. It is only when you build the structure stiffness matrix and you take the KAA part that it will not be singular normally unless you have a instability caused by buckling. You follow? So there must be some value of P which will reduce the flexural stiffness to an unstable situation. So how do we generate the stiffness matrix for the structure? Well, first you need the transformation matrices, and they are simple, we have done this before, they are identity matrices. You have to correctly put the linking coordinates, very clearly it is 3, 4, 1, 2 for the first element and 1, 2, 5, 6 for the second element in case A. In case B what will happen? The same T1, T2 but the linking coordinates will be, you have to be careful. It should be written as 5, 3, 1, 2, right? 5, 3, 1, 2. Okay, yeah, so that we need to do. Then you generate the structure stiffness matrix. Case A both ends fixed. Please note that minus P stands out in the geometric part, and second case both ends pinned, you can easily generate this, okay, right. What do you do next? You have got the KA for both of them. Let us take the first case first. What do? You write down the determinant, that is it. So this is your, and you can see very clearly why the determinant should be 0. If you go back to case A, this is, look at the top left hand corner, KA is that portion on the left, and for the secondary it is minus P into that portion. So it is going to look like this, and if you expand it, that is the equation you get when you write down the equilibrium equation, because there is no external load acting on it. P is a load which is implicitly there, but there is no F1 and there is no F2, it is just a actually loaded column, there is no F1, F2. So this can have a trivial solution. What is a trivial solution? D1 equals 0, D2 equals 0, which means the column remains straight, no buckling. So if you want a non-trivial solution, that determinant has to be 0. Is it clear? That is how we say that determinant. So if you made equal to 0, you will get an equation. That equation is called, that is your characteristic equation, okay, that is the characteristic equation. How many solutions will you get for that? It is a 2 by 2 matrix. So you have 2 solutions. What are those solutions called? They are called eigenvalues. They are called eigenvalues, and we are really interested in the lower of the 2 because buckling will take place at the lower load, right. So you can solve that equation and pick up the lower value, and you have got an answer, and the exact answer is 4 pi squared EI by L squared, which turns out to be 39.478. You got 40. Is that good enough for an engineer? Fantastic, right. But you will get a better solution if you had 3 or 4 elements, right. Similarly, you do it for both ends pinned, you have now 4 by 4, you get 4 eigenvalues, but can we simplify this? You can if you make some assumptions. You have a rough idea of what that first mode shape is going to be. So is there any relationships between D1, D2, D3, D4 that you can intelligently utilize? What can you say looking at the mode shape of a pinned? D3 is equal to minus D4 because it is equal and opposite, yes, because of symmetry. What else can you say? Because of symmetry, D2 is 0. So can we reduce this to a 2 by 2 form? Yes, you can, you can plug in wherever you see D3 and D4, you take one of them, you write D4 is equal to minus D3, so you got rid of D4. Wherever you have D2 you put it equal to 0 and you rewrite, expand and rewrite those matrices. This is called condensation, it is called static condensation. In matrix methods this is one technique of reducing the size of your matrix when you have interrelationships in your displacement vector. So you do that, exactly what you said, you do that, and then if you expand it out it will reduce to this form. Okay, you have only D1 and D3, you got rid of D4 and you got rid of D2. Now you take the determinant of this, take its eigenvalue, the lower value, you get 9.944. What's the exact answer? Pi squared EI, that's 9.869. Okay, so some error there. And if you want the mode shapes, you get them also, except that when you have two elements you just get one delta. It does not really help you, but still you can try to plot it. You do not know the curvature of those lines, right. So we are guessing that it is going to look like this because we know the slopes have to be 0 at the two ends in case A. But if you really want to generate that mode shape more correctly in a case you did not know, what would you need to do? Here you have only delta and 0 0, so you could join with a straight line if you wish, but that is wrong. So if you wanted let us say I want the value at a quarter span point in relation to delta, what should I do? I just need to create a node there, which means if I have 4 elements I get the quarter span displacements in relation to the mid span. You understand? That is how I do it if I really want to know the mode shape. Is it clear? But in the exact solution, eigen solution, you get the mode shape nicely as a sinusoidal function. So that is more exact, that gives you the mode shape value at all the points on the beam. Okay. Let us demonstrate with a portal frame. Okay, it is an unsymmetrically loaded portal frame. Typically how you find the buckling load is you have to keep incrementing the loads. Let us say you start with 0 but you keep that proportionality, you know, if on at C you are applying P, at B it should be 2 times whatever you are applying, and if you were to do an experiment you keep loading it, maintaining that ratio, that is called a load factor, by the way. So if you had loads all over the place, you multiply all by the same factor, keep building it up, and at some point what is going to happen? It is going to buckle. Okay, and most likely this is the shape it is going to take, right. Now your job is to find that critical buckling load. What is P critical? What is P critical? So how do we do this? Well, the procedure is exactly the same and we can have some guesses. Can you guess some initial values? In that frame, which of the two columns will govern the buckling load? The left one or the right one? Left. Why? Because it is more heavily loaded and the length is the same and the cross sections are the same, so the left one. So what are the limiting values that you expect for that left one?
Free then 0.5.
It depends. You can remove the left one and put a rotational spring at B to take care of the remaining portion B, C, D, and the stiffness can have two extreme values to get you the lower and upper bounds. One is 0 when it is a cantilever. For a cantilever what will be the KE? Cantilever?
Y4.
Cantilever KE will be 2. Effective length ratio is 2 times, you know that. We have done this problem earlier. And if it is fully fixed, come on, it is an unbraced frame.
1.5.
Just look at the deflected shape, there is going to be a chord rotation, it will be 1. Okay, so those are your limits, you should be able to guess them correctly. Ke will be either 2 or 1, most likely it will be somewhere in between, you have to find out the value. Okay, so you must always as an engineer have a guess, have an initial guess of what the likely load is. Okay, so you write down the, this is a slide I am picking up from what we did when we did portal frames without any beam column effect. without any p delta effect. So this is straight from that, you have 6 degrees of freedom which are active and 6 which are restrained. You can generate the TI matrix for all of them. We have done this before, 3 elements, but now when you write down the stiffness matrix you have to make a small correction for P. But do you know P? Yes, we know, one is P. There is a P for element 1 which is 2P, and for element 3 it is P. What about element 2? Will it have any force at the point of buckling? In the deflected shape you may get some force, right? Okay, this is what you need to do for all the elements, but you have to put in the correct value of P. Okay, now you may get an actual force in BC, but it's very minimal. So this is one convenient assumption we always do in beam columns. You worry about the effect of axial load only when the axial load is significant. If it's a very small, so in beams we usually ignore it, in columns you have to. Now for example here that 2P can come from the floors. Let us say this is a 20-storied building and I am trying to simulate the lowermost story, then that is the weight of all the floors coming from above. Is it clear? So these are the kind of physical meanings you can have. So we are saying P1 is 2P, P2 is 0 and P3 is P. Once you know this and you know the properties of elements 1, 2 and 3 which we have already derived, you can derive the 3 element stiffness matrices. For element 2 it is exactly what we had earlier, no change. For element 1 and 3 it is going to change and P comes into play, right. You have to just write down that Ki O star plus Ki G star. So when you add it all together it takes this form. Is it clear for elements 1 and 3? Then you assemble the structure stiffness matrix exactly the same way we did earlier, and you can write it in this form, and it is exactly the same procedure, only thing an unknown P comes into the picture. Finally you get Ka in this form, that is all you need, you do not need Kar and Krr. And if you want to get the correct answer, then you must find the determinant of this matrix, right. Now you are going to deal with very large numbers, you can see there, because 565 etc., you got 6 digits out there. So it is good to work with another alternative measure of the critical buckling load. So let us bring in lambda, which we can call P by EI of any of those columns, EI1 or EI3, they are both the same, and when you do that your equation simplifies to this format. Okay, if you divide throughout, if you normalize it, it is the same equation. See, whether the determinant of the first matrix vanishes or an equivalent matrix vanishes, it is the same, it will give you the same result, but you are working with a better value. We have brought in a lambda into the picture. We just divided the P by EI, which means divide all the values by EI, you will automatically get lambda in the picture. And now what do we do? What method do we use to get lambda? You get 6 eigenvalues in this. We are not interested in all 6, we are happy with the first one. If it is a dynamics problem, by the way dynamics is similar to instability in this respect, then you may be interested in higher eigenvalues also, because they get excited, higher natural frequencies get excited by arbitrary loading, but in buckling you do not have that problem, it will fail. Some people made this suggestion, look, if I have a column let us say pinned and I apply a load here, it is going to buckle like that, right. So maybe I will hold it in the middle, and once I hold it in the middle and prevent it from laterally moving in the middle, it goes to the second mode before it buckles. So if I go to a slightly higher value than P, let us say I put 2 times P, then I remove my hands, maybe it will stand. Well, theoretically it will stand, but experimentally it has been proved that it does not work. There is no way it is going to go back and fail in the first mode. So the lowest mode will always dictate the capacity of the structure. Okay. So here what you can do is you can do something like the bisection method, but you need some trial values. You have no idea how to pick them up. You do not know whether, well, you can start somewhere, start with the lowest buckling load. So we want to find out what gives you the lowest value. So you remember the lowest is when AB behaves like a cantilever. So you can easily find out for that, when it is a cantilever, what is the value of lambda. Now if you put this value of lambda into that expression for the determinant G of lambda, will it be positive or negative? In the bisection method you need to figure that out. So you do not know until you put it in that value. So put it in, and you can find the determinant easily by MATLAB. It turns out to be positive, you get some value plus something. Okay, so now you need to trap another value which is negative. Now you need not go to the other extreme. So how do you get the next value? What is a clever way of doing it? You do not need to go to the upper bound, you have to kick. So what should you do cleverly? Do trial and error, few trials are enough. What is the next trial you will take? Well, double, I mean work with round numbers. Try lambda equal to 2, try lambda equal to 3, try lambda equal to 4, because we do not want it exactly, we are doing bisection method, we just want the nearest positive value. So you do that little exercise, increment it say in steps of 1, you will find when you put lambda equal to, okay, in this case 0.1, because 0.077 is very low. At 0.4 you are going to hit a negative value, at 0.3 it will still be positive, you can check it out. So now you can do the bisection method, right? You have got the two values, you know that lambda critical is between 0.077 and 0.4, and you do the bisection method, you can get the correct value of lambda critical, and you get the solution as 6072 kilonewton. That is it, okay. It is a little approximate because we are using that function, we are using the concept of geometric stiffness. If you want more accuracy, put in some more nodes, one more node and check it out, but this is reasonably good. So this is how you can do instability analysis for any structure. We do not have time to do a second order analysis, but this is explained at length in the book. What do you need to do? Let us take a problem like this, I am not going to solve it, but at least let us figure out how to solve it. So you have got a load at the midspan 1000 kilonewton, you have also got a lateral load 100 kilonewton, the frame is the same frame which we analyzed earlier. Well, the first thing you should do is carry out a conventional first order analysis and find out the actual forces in the 3 elements. You will get it automatically from the program that you have developed for analyzing plane frames, so you will get it. Then you take those actual forces which you got and modify the geometric stiffness matrix, okay, right, and run it again, you get a solution, another solution. Will that be correct? Why not? Well, it is a reasonably correct solution, but if you want more accuracy, you should check out the actual forces you now get. Okay, so typically nonlinear analysis is like this, you do not know the actual forces, but you get a first order understanding when you do one run, then you pick up the value, modify the stiffnesses with those values, do a second run, you can do a third run usually with 2 or 3 runs, and anyway the computer is doing it, you are not doing it, the effort needed is just to program it, you have a tolerance level and that gives you your complete solution. So this is demonstrated in the book, you can do any number of problems of this type. So my friends, we have come to the end. Okay, this is the last technical lecture we are having. If you look carefully, what did we do in advanced structural analysis? First two modules we actually reviewed basic structural analysis. In the first module we actually looked at an introduction to what we do in structural analysis. Specifically we looked at statically determinate structures, how to find the force response in statically determinate structures. We looked at typical beams, trusses, arches, funicular arches, cable systems, plane frames. We also briefly looked at space frames and space trusses, right. Then we looked at ways of finding displacements, okay, deflections in trusses, deflections in beams, rotations, curvatures in beams and frames. And we did this by many methods, but we found that the most powerful and general method is that of by the principle of virtual work. And then we looked at other energy theorems which could handle both statics problems and kinematics problems, and they had their equivalent work theorems. You had the principle of virtual displacements, principle of virtual forces. Then in the second review we spent a lot of time on indeterminate structures. We first looked at statically indeterminate structures, and we looked at complex problems including elastic supports and grids and so on. Then we did, and that is a new thing, I think it's a topic which I believe is not very well learnt in many universities, displacement methods. Okay, we did not study them independently, we looked at them together. We did an introduction to displacement methods, then we looked at slope deflection method and moment distribution method, and the real thing we learnt is how we can dramatically bring down the degree of kinematic indeterminacy by having a feel for the structural response, taking advantage of releases, guided fixed supports and hinge supports. We also looked at how you can deal with frames which had symmetry subject to lateral loading, how you can simplify the analysis. We also looked at approximate methods of lateral load analysis. So we did all that. Then we got into matrix methods. We first did a mathematical review of basic concepts. Now you see all those concepts have been used, including eigenvalues, all the way to the end. It's basically linear algebra. Then when you first saw that, you were not very comfortable because trying to solve structural analysis problems with matrices looked daunting. We looked at powerful transformations, we looked at the contragradient principles and the general theory, that is in the third module, and we specifically went into every type of structure. We went into trusses, axial elements, we went into space trusses in module 4, we looked at beams and grids in module 5, we looked at plane and space frames in module 6, and in this module we took a kind of overview. We did not go too deep, but we have a clear idea what to do when you have to worry about elastic instability and second order effects. So 40 lectures, one more lecture to go, that is a general lecture, but to remind you, I have written 2 books and we have used the material in this book, these 2 books for the study. You need to look at those books to really understand what is going on. And with that, this is just to tell you that the paperback edition is available in India, published by Narosa in 2008 and 2009, and the international edition is hardbound, published by Alpha Science from Oxford, UK. And that is it. Thank you very much. Before I end, I also want to place on record the tremendous help I got from Najib Sharif. Sharif, stand up, give him a hand. He's my MS student, he's been the TA who helped us in this. I am grateful to the staff of NPTEL, without whose support we wouldn't have been able to do this. In particular, I wish to place on record the support given by Manikandan, who is not here, who is the one who made many of the slides that you have access to. Thank you very much. Bye.